I will be talking about text to 3D scene generation. So this is kind of going in the opposite direction as the previous talk. And the basic idea is that we would want to connect language to the world. And some of you may be familiar with this little excerpt here. This is an excerpt taken from the game Zork. It's describing a scene. You are standing in an open field west of a White House with a boarded front door. There is a small mailbox here. And what we would like to do is we would like to be able to generate a 3D scene that reflects that image, that text description. So this is a pretty hard task. And our goal is to be able to generate these 3D scenes from natural sounding text. As an example, if I give you this sentence, there's a couch and a TV in a living room, we would like to perhaps generate a scene like this. This is our actual output from our system. And the key insight is that for natural text, it doesn't state everything that should be in the scene. It basically places some constraints on what should be in the scene, but we need a lot of prior knowledge to infer the implicit and unstated constraints. For instance, this sentence indicates there should be a couch and a TV, and there should be a living room, but what should go in a living room? There's usually additional objects such as bookcases, and for the TV, perhaps it should have a TV stand on which it's placed. So before I start, I want to kind of talk about a bit of prior work that's relevant. Many of you are probably familiar with the very famous Shoodaloo system by Terry Winograd from the early 70s. So he had a nice system where he worked with basic geometric blocks. And the system had a lot of prior knowledge about the shapes, colors, and even physical support and containment of understanding of these objects. And you could do interesting things with the computer. If you refer to, like, for instance, the grasp of the pyramid, the system will actually ask you to disambiguate which pyramid you meant. More recently, there's the Bird's Eye system. This is a SIGGRAPH paper from 2001, and here is an example scene generated by them with a zebra and a barn that's 20 feet behind the zebra. And if we've been continuing work on this, and here's a more recent scene, this is actually a little crop from a much larger scene. But in this scene, you will notice that the language that's used to describe this is fairly verbose. In addition, it contains some unnatural language, such as indicating the chair has to be facing north, and that the stapler is 1 foot to the right of the computer. This is not language that we typically use when describing things. So the reason this task is very hard is that it's hard to figure out, like, what objects should be in the scene, and if we need this prior knowledge, how are we gonna go about to get that? And how do we actually do the final layout? So in this talk, I will present a framework for thinking about this problem and discuss how do we use prior knowledge and learn from data to help. To start with the first challenge, we will be treating text as a constraint, and we will do parsing to determine what objects and constraints must exist. And then we will use prior knowledge that we have learned from scenes that we have observed to infer unstated implicit facts. And you can infer this prior knowledge from other sources of information, such as images and text. For this talk, it will be inferred from our data set of 3D scenes. And then, in addition, we will discuss how this is actually incorporated into the system for inference, and to actually lay out and generate our things. I start with a brief overview of the framework and some of the representation that we will be using. So given a sentence like there is a room with a table and a cake, there's a red chair to the right of the table, we want to be able to first generate, this is what I call a scene template, where it's basically a graph where the nodes indicates the objects and the edges indicates the relationship between the objects. And these are basically just the objects that has been stated in the description. From that scene template, we want to basically perform inference and infer from objects that are not stated. In this example, we have inferred that perhaps there should be a plate. And in addition, we want to infer additional relationships, such as that the cake should be supported by the plate and the plate supported by the table. And finally, from a complete scene template, we should be able to select models that represent our objects and arrange them to form a possible scene to be presented to the user. So I start with constraint parsing, in which we want to identify the explicitly stated objects and relations. So we start with a piece of text. There's a piece of cake on the wooden table, and we use the Stanford Core NLP pipeline to tag and parse the text. And we look for nouns, noun phrases, for candidate objects to visualize. In this case, we've identified 3 items, piece, cake, and table. And you'll notice piece is not actually visualizable, so we'll filter that. This can be done with either a list of categories of visualizable objects or by using WordNet for physical and objects. And then next we will identify relations and attributes by looking at modifiers and dependency paths. And we will extract things like, oh, the cake should be on the table and the table should be made of wood. I'm not going to go into the details of how this is done, but it's just using some simple rules explained in the paper. And one thing that we have to do is once we've extracted these constraints, we have to interpret what they mean and how do we actually, for instance, what does on mean? Here I show some possible interpretations of on. This is actually also some things that our system generates. But you'll notice, this putting a cup on the table is very different from a poster on the wall. And we will learn how to do this by having a data set where we have 3D scenes and we've marked 2 objects, one in green and one in purple, and we ask the Turkers to indicate the relationship between the 2 objects. And using this data set, we're able to learn a geometric interpretation of the relationship. We do this using a fairly simple method. We basically take the top 15 keywords from the aggregated user responses as our relations, and for each relation, we then train a logistic regression classifier indicating how likely 2 objects in a scene are to have that relation. And our features are geometric features such as the relative position between the 2 objects and whether another object is physically supported by some other object. And this figure here shows some examples of the distributions we learned for some of the spatial keywords, like above, it's above the table, and left, right, and front, behind. So, and after this, so we also learned that the on is basically corresponds to the support to feature. And so now we know that the cake should go on the table, and then maybe we can generate some image like this. But the cake is maybe a bit too big and the table a bit too small, so this is not quite what we want. What we want to do is have a fuller picture of what's going on. And so we want to basically be able to generate or infer other missing objects, such as there should be maybe a plate, and the cake should go on the plate, and the plate on the table. So how do we do this? We do this by using prior knowledge, and we get this prior knowledge by learning it from data. This is another example of, why you need prior knowledge, and the size is one of those most important. And we start with having a model database. And this model database is basically a set of 3D models connected from the Trimble 3D warehouse. And it has been manually annotated with the category, the semantic orientation of the objects, like the font, the right, left. And for the sides, we have, in prior work, we have done semi-automatic annotation of it. I'm not going to go into details, but basically we look at furniture catalogs to get an estimate of the size, and then propagate via categories to other models. In addition, we have a database of scenes. Scenes are a very rich source of information. From scenes, you can get information such as object co-occurrences. We have basically a notion of a scene type. For instance, this scene is a living room, that one a dining room. Or it could be even simpler. The scene model shows a dining table. And in this example, by counting up the number of dining table scenes in which a table occurs, we can get that table should always appear. And then plate maybe just 90% of the time, and cake maybe just 10% of the time, and so forth. And in addition, from looking at scenes, we can also get a support hierarchy, or a probability that, if I'm a table, what am I likely to be supported by? This is also done via simple counting, and we just basically observe. And using these things, we can basically have, this is an example for learned prior of where we show that, for instance, for a desk, maybe you'll find a keyboard is on the desk 60% of the time. Here are some more visualizations where the red indicates area of strong likelihood. A lamp is likely to be found on the floor. A desk lamp, however, is just probably likely to be found on the desk, poster maybe on the wall, and plate on a table. And similarly, we can use the scenes to get priors where how things should be oriented with respect to each other. Like if you have a bunch of dining tables, you can observe, the chairs go around it. And this is, again, a visualization of our learned distributions. So here, if we ask the system where would the chair go with respect to the table, it would be here. Poster would be here along the wall, and mouse and keyboard would be most likely there. So this information, once we've gathered these priors, we can now use it in our scenes to infer unstated facts. And so now we're going to see how we can do that. First, we want to identify missing objects. And to do this, we basically just take our probability and kind of use base 1, flip it around to figure out, okay, we have cake and table, what is our scene type? We'll just take the maximum, and that gives us a dining table. And based on the scene type, then we can identify plausible other objects, such as plate, fork, cup. And so now we just add some objects that are likely to occur. After we have the objects, we would like to identify the support hierarchy. And to do so, we basically just select an object that exists in the scene that maximizes our support prior. And in this case, we will get a figure like so, where the cake is on the plate and is on the table. Finally, we want to take out these objects and actually figure out how to visualize them. And going back a bit, we basically have for each object, in addition to the category and attributes, a combined keywords that we will use to look up in the database. And we query our model database, and we get some models to represent our objects. And finally, we lay them out and arranging the object so that it maximizes our layout score, which is basically a function of our priors on the relative position of objects and constraints. For instance, if something has to be to the left or right of something else. I'm not going to go into the details of this, but that's the general idea we want. I'll show you some example results. So there's a room with a desk and lamp. There's a chair to the right of the desk. Notice that this is the scene hierarchy. Notice that we're able to infer that the lamp goes on top of the desk without the user having to specify that. And there's a room with a computer and a red chair. And notice that we're able to infer that, okay, maybe there should be a desk that supports the computer. Here are some comparisons of what would happen if we didn't have priors. If there's no priors, and there's a desk, a keyboard, and monitor, maybe everything just goes on the floor. If we have support hierarchy, what happens is that maybe the monitor and keyboard are on the desk, but it's not nicely arranged. If we have relative positions, then we get a more reasonable scene. Similarly, we can see that having a good grounding for spatial relations is important. If we don't know about spatial relations, and we have this sentence in which the coffee table, the chair is in front of the coffee table, and the lamp is behind the coffee table, we have this. If we have a naive predefined relation, we get the chair is here, the coffee table is kind of in the back but to the side, and the lamp is to the back. Then with our learned relations, the coffee table is more appropriately directed back of the chair. So this is a really, really hard problem, and our system is not really that good. There's many failure cases. Here, there's 2 plates on the table, but they're kind of overhanging a bit. And here we have this sentences, there's a box of donuts on the table. We have a table, we have a box. There are no donuts in our box. Instead, there's one huge donut on the table. So it's challenging. And then there's some other failure cases where we put a desk on the roof. Desks don't go on the roof. And there's a trash can, just clinging to the wall. So this is a hard problem. And to conclude, it's a hard problem, but I think it's very interesting, and we've just barely scratched the surface. And I would, like to summarize, we've shown that, it's with explicit constraints is important, but you can have more complicated text. And for instance, if you have a sentence like the red velvet chair with golden arms in the king's room, how would you interpret that, and how would you find the appropriate object? And we've had an initial start of, some kind of implicit facts we can infer, but again, there's much more improved spatial priors and complicated things. For instance, if I say Tom's messy office, for now, I think if I were to generate an office, it would be messy, but again, what does that mean? What should I have? And then just turning the constraints and actually doing the layout is also very complicated. And like a sentence like the chair around the table had been pushed over, that's difficult. So for future work, we're focusing on doing a more quantitative evaluation of generated scenes, and we would like to create a data set of scenes and corresponding text descriptions so that maybe other people can also work on this task. And basically, I think this is a very interesting task, and I would like to hopefully inspire all of you to maybe work on this, and maybe one day we'll be able to do this. And thank you all for coming, and we have a project website with an online demo. It doesn't have everything I talked about here. It mainly has the support structures, and it's a bit slow, but you can visit and try it out.
Thank you. Let's thank the speaker. Questions?
Thanks for the nice talk. Assuming you are picking the argmax scene as an output of your model, how do you define the viewpoint, which is the correct viewpoint or most likely viewpoint of your output?
So currently, the system will start with an initial viewpoint, and it will stick with it, and it will arrange the objects. For instance, if you have left or right, it will just arrange the objects so that from that viewpoint, if you say a chair is to the right of the table, it will stick with that one viewpoint and arrange the objects so that the chair is to the right of the table. Yeah.
Then semantic size and semantic orientation is irrelevant from the viewpoint?
So I guess this gets into like so currently the system assumes that phrases like to the left and to the right are from a viewer-centric point of view. But our interesting line of research would be to see when it's from a viewer-centric point of view and when a phrase would be from a allocentric or object-centric point of view. For instance, if you say the chair is in front of the table, you probably mean that it's in front of the table, like it has a certain arrangement regardless of the viewpoint. Yeah.
I have one more question. So when you're learning prior knowledge based on semantics, how do you differentiate between table versus dining table?
So currently I'm using these manually created set of scenes. So objects in these scenes, the models themselves have annotations that indicate whether they are dining table or not. And the table is considered a superclass of a dining table. So anything that's a dining table is also considered a table. So does that kind of answer?
If you have a text that doesn't represent actually the object, for example, if you don't have the object already drawn with you, what do you do in this case?
So you're saying if I don't have a model for that object?
Yeah, right.
Currently I don't. I think it just finds the closest matching object, which may be totally incorrect.
Thank you.
So about the spatial, the position in the space. So some objects, because I see there is a physics is that something in the air, it should be on the ground, right?
Yes.
So this kind of position, I don't know how do you get this kind of information and how to inject this information into a training, into a model?
So right now I have a data set of 3D scenes, and currently all the priors of where things should be and where things should be positioned comes from observing it in that data set. And so that also means that for certain objects, if we didn't observe it in the data set, we kind of assume it goes on the floor because that's what happens most of the time. But sometimes, it may also just make a bad decision. Yeah.
So basically it means that you store some prior information as a database, some knowledge base to store the what kind of position should the object at. Right.
Yeah, so what we do is from the data set of scenes, we then learn this set of priors of where things should go.
I see. So do you have some plan to learn such kind of spatial relationship from the real images?
So I guess I feel like vision is hard, so that's why currently I'm not trying to learn from images, but I think there's also a lot more images than the 3D scenes. So it is actually a good source of data.
Yeah, I just feel that it is very difficult for manually to specify, to store, to manage this kind of spatial information database. If you can learn it from the massive amount of the real image, you can find this kind of relationship, and that may help you.
So I guess to clarify, I'm currently using it's a small data set of scenes, 3D scenes. So it's not directly a database. And
I see you have a set of the 3D things to learn this kind of relationship.
yes,
I see.
yes. The data set is fairly small. It has about 133 scenes, but we are planning to expand that. And it is still true that there's a lot more images.
Okay, thank you.
Okay, thank you. Thank the speaker and all the speakers of this session and all the people who asked questions. Thank you very much. And we are done.